All right, stage is yours. Dennis.
Yeah, thank you, Yasin. So let me just share my screen. Okay. Can you see my screen?
Yes, we see it.
Okay, so hello everyone again. I'm Dennis, and I'm gonna present you MRLN's midpoint milestones. Um, so to basically give a brief introduction to MRLN, it's basically a on-chain tool and a zk gadget for spam prevention and rate limiting in anonymous environments. So this idea and the project was found by Ethereum Foundation Privacy and Scaling Explorations team, but I wanted to explore and see how to build a native one on Mina using O1.js. So in anonymous environments, no one knows who used the system, and it's only possible to interact if a zk proof of membership is valid. And this also brings, it's not possible to prevent a spammer interacting if they are registered to the system. So rate limiting nullifiers, they basically bring a financial mechanism to prevent denial of service attacks and also provide spam preventions. But before explaining how MRLN works, let me just introduce you Shamir secret sharing. So it's a cryptographic scheme which allows to split a secret into n parts and recover it by providing any k parts where k is smaller than or equals to n. And under the hood, it uses Lagrange interpolation, which is a well-known mathematical concept. And a polynomial of nth degree can be recovered from n plus one of its evaluations. For example, you can draw a straight line with 2 points. So which means a straight line means a linear polynomial here, which is something like y equals to a times x plus b, since it's a one first degree polynomial. And if we set f0 equals to s, where s is our secret, and other coefficients to random numbers, we can evaluate the polynomial at random points as many times as the amount of shares we need. So with this, how does MRLN work? So it's basically a combination of proof of membership plus Shamir secret sharing. You can limit number of interactions with the system per epoch, where epoch is some period of time, for example, 1 interaction per second. And you can think this as a slow down mode or on Discord or any other social application. And so here we have a polynomial, which is like here in the example we have a linear polynomial, and which is and we have a0 here, which is the secret, and we have a1 here, which is the Poseidon hash of a0 and epoch. And with this, we don't need to generate a new polynomial for every epoch, as the coefficient is derived by hashing secret and epoch together. And so my midpoint milestones are basically building a circuit to accommodate different rate limits, and also in having an initial implementation of the MRLN contract. So here you can see the MRLN circuit overview. We have epoch, we have message, and the secret going in. And the center part here is basically this Shamir secret sharing scheme. The right side is the construction of identity commitment, which is basically the public identifier for being anonymous. And the left side is constructing nullifiers, which you can think something equivalent as nonces. And we get a zk proof afterwards for proving that your epoch and message are accurate and verified, and it also proves that you are you are a member in the membership group, and the circuit spits out a secret share, and which is the most important part of this, because it's used in Shamir secret sharing, obviously. And yeah, let me just open VS Code and let's go through the code here. Yeah, so here you can see the RLN circuit written in O1.js. So first we get a secret as a private input, and we hash it for getting the identity commitment. And we also have another rate commitment where we hash the identity commitment and the message limit together. I will talk about the commitments in a more detailed way later on, but let me just first introduce the circuit. So we do a membership check here. Also, it's known as semaphore on EVM ecosystems. And then we do a Shamir secret calculation, as I explained before. And also we calculate the nullifier here. So here you can see the external nullifier, and this is basically the Poseidon hash of epoch and the RLN identifier. And here the RLN identifier is basically a random finite field value, and it's unique per RLN application. So it's required so that the user can securely use the same private key in different RLN applications with the same and this also allows user to have different values of the coefficient A1, because as you remember, A1 is basically the hash of A1 is basically the hash of epoch, and A0, and A0 is secret here. So it basically makes the polynomial different. And yeah, so here we see the RLN contract, and we have a constructor to set a bunch of different variables, because as I mentioned, fees play an important role in the economical side of the protocol, because that's how we can prevent spams and prevent denial of service attacks in an on-chain manner. So these variables also prevent self-flashing attack vector by making it economically inefficient, and also the concept of fees prevent money laundering schemes, because a user or a person can register to the system by staking, and also they can just try to slash themselves to get the money from a different wallet just by providing a zk proof. And this scheme can be used as a money laundering scheme. So to prevent this, we the PSC team built a mechanism for that, a fee mechanism for that. And yeah, so in the registration function, we enable different rate limits for different users based on their staking amount, and we do this by having a message limit. And we find this message limit by dividing the amount by a minimal deposit that we define in the constructor. And it's also important to understand that we may not want to have like different rate limits for different users. So we can enforce that by setting the hard value of stake amount. And then we get the identity commitment, and we just append it to the user set. And yeah, we also check that the set must not be full. And that's all we do for registration. And we also have another function for withdrawing, releasing, and slashing. But before getting to them, let me just explain. Oh yeah, I can actually start with explaining withdraw. So for withdraw, this function is basically functions as withdrawing functions as a request for withdrawing and freezing the stake to prevent self-slashing, because the stake can be released after the freeze period blocks. And we again define these blocks here in the constructor. And so it's also important to differentiate the two terms, withdrawing and slashing, in the RLN protocol, because withdraw, when the account that withdraws an identity commitment and the stake is the same that registered it. But in slashing, it's when the account that withdraws an identity commitment and stake is different to the one that registered it. And it's important to separate these terms, because in withdraw method, users don't have to pay fees. And the reason is if it's the same account that's used the withdrawal, then it's clearly not a money laundering. But that's not the case with slashing, and that's why users pay fee for slashing. So self-slashing is not a problem, because users will still lose some amount of their stake. So it's economically inefficient for people to try this protocol using as a money laundering scheme. And that's why we have separate functions as release, withdraw, and slash. and yeah, and in slash function we just slash the identity with identity commitment, and we just delete it from this user set we have. Yeah, and I guess that's all from my point. And please don't hesitate to ask if you have any further questions.
All right, thanks, Dennis. Do we have any questions from our crowd? Yes, we have one question in chat.
Yeah, so I couldn't finish writing the test yet, so I can show you a proof of concept for generating a nullifier. Yeah, but it's basically, nullifier is basically the hash of so nullifier is basically the hash of the secret. Yeah, it's basically the hash of the secret, the external nullifier, and the message ID itself.
All right, thanks, Dennis. Any more questions? Yeah. Any more questions or comments?
Oh, no. It's not something related with any wallets, because this MRLN scheme is built for preventing rate limiting and spam prevention in anonymous environments. So it has nothing to do with wallets. It's just so for registration purposes, it works like a semaphore group. So you just take some amount and you have a secret value that you define it by yourself. You can think it as a password or something, and you just hash it by Poseidon, and you just provided the contract, and that's how you can just get registered to the system. And in the circuit, you prove that you are a proof of member. In the circuit, you prove that you are registered in this set. So that's how it works, basically. Yeah, definitely. Actually, Waku uses the Ethereum implementation of this, which is built by the PSC team. So Waku uses MRLN too, yeah.
All right. Thanks for addressing the questions, Dennis. I think it's...
Thank you.
So yeah, last call for questions. Normally we would have the Chlorio team to present, but they've been in they've been issuing some... Yeah, that's a nice idea, Mohammed. So they've been the team has been facing some technical issues. That's why they send a pre-recorded video. So I will send the pre-recorded video to reviewers. That's why this is the end of this session. Yeah, thanks all for joining, and I'll see some of you in the next session. And thanks again to our builders, and I will update you with the process. See you all. Bye-bye.
Thank you, everyone.
Thank you.
Thanks,
Bye-bye.
Yassine.